SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. This module 3 is on the structural mechanics, and we are in the last lecture on the module 3, that is the lecture number 15 in serial, and the topic of this lecture is theory of column. So, in this particular lecture I am going to cover the following concept. We will introduce this particular subject, and then we will classify the column first, and the Euler's theory of the long column we will discuss, and concept of equivalent length and the concept of slenderness ratio we will discuss with some numerical example. So, learning objective of this particular course will be that we will discuss the type of column and its structural implications, and also will outline the stability of the long column, which is one of the critical issue for the column, the stability issue, and we will try to apply the concept of the slenderness ratio in the analysis of column. This is one of the prime factor to analyze a column. So, first let us go to the initial discussion on column. Column or pillar, everybody knows what is that. Today in the society, in our society, there are buildings coming up here and there, RCC buildings, sometimes it is also some of the steel buildings coming up. So, you must have seen the particular building comes up from the foundation to the roof, and when it is coming up as a structures, first they have actually construct the structures, they construct the foundation and the column. Columns are nothing but the vertical element of the any structural systems, and this is actually going to support the beams and the slab, and the prime objective of the column is to transmit all the superstructural load or load from the beam practically to the finally in the grounded, it has to be finally transmit to the foundation. Primarily it is a column is a compression member. As a nature, you see, if you have some load on a top of a particular stick, this particular stick is act as a column, and that is definitely under a compression. It will not going to be a tension member, but yes, depending upon the location of the column and depending upon the associated load between the two sides or the adjacent side, or maybe there is a third side, column is also experience some bending. So, in case of the monolithic construction, when there is a two side beam and the cross beams are monolithically casted with the column, there may be kind of a rotation occur in the column head, and due to the rotation occur in the column head, there may be kind of a bending occur, and those bendings are uniaxial bending, and there may be a biaxial bending is also there, and that will be that is not in our scope to discuss, and that can be tackled in the finally in the designer when they design the column, they analyze and then design. Column is also act as another element in architecture, that is very strong visual element in particularly in the elevation. In the era, in the early civilization from the Egyptian age to Roman, or also from the Greek, then anywhere if you see, even in the modern architecture also, column is also used as a prominent architectural elevational element, and it is sometimes so dominating. You see these two pictures, one is the Parthenon in Athens, which is the early example, and another one is the British Museum London, which is also a early medieval example of a building. So, those buildings if you see in the first look, if you see, is the prominent column, that mega column, I can say that the so huge, so tall columns gives you a kind of a impression of the particular building, and that is it's create a kind of a iconic structure. It will actually create a iconic structure kind of a feeling. So, again if you go back to a history of architecture and if you see there are different type of column, capital point of view or the total the proportion point of view from the capital and the shaft and also the base from the capital or arrangement ornamentation point of view, column can be there is 3 orders in the Greek column particularly. So, it is not the classification of the column, but there are 3 orders you can say because of the proportional systems, Doric, Ionic and then Corinthian order, and as you all know I am not going to detail of it, but that is also one of the character of the column. As and when the things grow up, the building has become very much elaborated, and that can be one of the point is the visually appealing, and another point is structural. Then when it will going to tall, and then there is a continuation and there is a kind of a shaft is may not be the perfectly the same dimension and the same radius, the radius increases towards the feet. So, from that point of view there are different order came and different type of the capital of the column is also it changes formation because of the bearing length is going to increase because of to take care of the higher amount of load also. So, from that point of view if you suddenly increase the capital it will look very odd. So, you have to make some kind of a ornamentation to hide that particular part, or may not be hide, may not be a right term, but you have to actually camouflage that one such a way that it create a proportional beauty on the column. So, from that point of view different type of capital is came, and for the different type of to the camouflage the structural requirement also. So, these are the some of the photograph I have taken from the net, and these photographs are of the some modern column. See, those we have just now seen in this last 2 pictures. Now, we have the modern era, the column are very slick, columns are having different type of definitions, different type of dimensions, and it will actually give a visual appealing definitely, and it will create a kind of a wonderful amazing interiors by virtue of those elements, or so kind of a proportional the mushrooming or the tree kind of a enlargement in the capitals also. The first the central first top picture is a the main building of Indian Institute of Technology Roorkee building, which was constructed in the 19th century, and this particular building was also constructed by the British people, and you see that particular building also look these columns are also act as one of the prominent element of the particular building facade. So, those are the this particular era, and this the modern era has taken the column in a different dimension. Now, the classification of the column can be classified in many ways. In structurally there are 2 way of classify the column. The first and important way to classify the column is that the short column and the long column. So, short and long column are defined with the 2 dimensions of a column. One is the lateral dimension, that is the thickness or maybe the diameter or maybe the the cross sections. Those are the dimensions of the lateral dimensions, and another dimension is the length dimension. So, these 2 dimensions are determine that whether the column is a long or column is a short. So, short column, this ratio between the length and the lateral dimension. So, if I say in other way, the length by the lateral dimension, suppose it is d, okay, the diameter and the length are by diameter. If it is this dimension, if it is more than more than 12, it is look very bulky, and this is going to be this will be going to be short column. And in case of a long column, so I have just make a small mistake, is less. If it is less than, I'll in the PPT I will rectify that 12, then it is a short column, and if it is more than 12, then it is a long column. Ratio is high, then it's look slender. So, something like this is a long column, and whereas this is a short column. So, this is the D and this is the L, right. So, this is the and the short column is subject to the compressive stress and it is failed due to crashing, and the long column will subject to the critical stress and due to buckling. So, let me erase this and let me go to the. So, these are the bulky short column and this is a slender long column, and this will be going to crash. So, if there is a load, it will going to crash and it will going to give a compression failure, and in case of the long column, if you just put it, it will going to bend, it will buckle, and that load or the stress called the critical stress. We will understand, we will find out the how to find out the critical stress or so. There is another way of classification of the column, which is the braced column or the unbraced column. So, the braced and unbraced column are that, since braced column you have an additional member which will take care of your lateral stability. For the lateral stability, either there is a single diagonal member or maybe there is a brick wall. So, it may be infill brick wall, so it can take as a bracing, or it can be take any kind of a lateral load. So, any kind of a wind or maybe some earthquake load can be taken into account by this particular diagonals or the infill wall. But there are sometimes unbraced, there is nothing, suppose there is empty, there is only the beams and the columns, there is nothing inside, no bracing, no infill. So, that is the unbraced column. So, we have to see that this column itself is so strong that it can take the lateral load. So, if there is any lateral load comes, the column has to take care of that. Now, let us go to the Euler's theory. Eulers was a mathematician. He has given a theory for the long column and he has developed a particular mathematical equation for the long column to solve, and that particular equation still today we are actually adopting for designing the analysis of the column. So, the long column, as I told, it is going to for a buckling, and it eventually it will, we have to find out the critical load. The critical load is conceptually found out something like that. If there is column is very straight, and if you just gradually increase the load, at a particular time it will going to buckle. It will not going to gradually buckle, it is a particular time it will going to buckle. If you just decrease the load, if the load is little bit less, it will not going to buckle. Just a particular fraction of point it will going to buckle, and this particular point where this is going to buckle is that is the critical load, and in that particular load the column become very unstable. For the stability point of view, so you have to put the load the lower than this critical load. So, we have to understand and we have to find out this particular how much is the critical load of the column. There are some parameters like geometric parameter of the column sections, that is that will be actually drive how much will be the critical load. The property of the column material, particularly the Young modulus of elasticity is one of the another character. The length of the column, the support condition, though there are 4 such parameter which will decide what will be the critical load of a column. So, there are different end conditions. So, suppose the columns are a hinge and hinge, both are the hinge. It can be definitely constructed in steel cases, steel building, steel column cases, but not in RCC. But there sometimes a column may be fixed and the free, simply kind of a thing. So, in those cases, there are other 2 cases also in the next slide. The column will going to buckle like this. So, at the hinge point there will be no moment 0. So, there will be kind of a, there will be some kind of a slope, there will also some kind of a slope, and the equation, the differential equation of the column will be like this. In case of a fixed and free, there will be 0 slope and it will bend like that. So, the equation of column will be like of the curvature or this particular profile of this particular this particular curvature profile after the loading will be like this differential equation. So, the differential equation is like this. In case of the fixed and fixed, both if they are fixed, they are bend like this, the differential equation is like this, and if it is a fixed and hinge, this is the differential equation. So, I am not going to solve those differential equations, it is very tough to solve, and of course, there are books you can see, there are type of the differential equation solve, there are mechanism, there are some methods. So, these differential forms are actually of this order you see the EI d2y dx2 equal to a into y plus b, something in this order, and the solutions of the differential equation, if you do and there are a lot of end conditions and the boundary conditions, we can find out the Euler's critical load, which is our intention to find out, is like this. The PE is the critical load of the column. So, if it is hinge and hinge, the critical load is pi square E I by L square. These three values are we are very familiar with. E is the Young modulus, which is for RCC is 1 into 10 to the power 4. In case of a steel, it is 2 into 10 to the power 5. So, we know the what is I is the moment of inertia of the section, that is we understood that how much is the moment of inertia, L by B d square and all those things are there, and the L is the length of the column, and there is always, you see, there are some 4 or some numbers, this is 1 upon 4, this is 1 upon 2. So, we can actually rewrite this all the Euler's critical equation or critical load equation like this, where the pi square EI will remain as same, and this L and this numerical value can be written as, and L is always L square here, you see. So, it is L E square, where L E is the equivalent length of the column, equivalent length. So, as if you see, if I say that the L E equal to L is the actual length, L is the actual length of the column, and L E is a fictitious length, which is a equivalent length, which is equal to L for hinge and hinge. For fixed and free, it is twice of L, that is why it is 4L square, and fixed and fixed is L by 2, that is why it is L square by 4, and fixed and hinge it is L by root 2, that is why L square by 2. So, this is the, you have to remember this formula, and you have to remember this 4 such equivalent length and the length comparison for the 4 different type of support system. So, then we can solve the problem, or you can actually go ahead. Now, we have to actually understood what is this equivalent length actually. So, I have taken a condition of fixed and hinge. As it is a fixed and hinge, after deformation it will have this is the hinge support, this is the hinge, this is the circle is there, this is a fixed. The slope will have some value, theta is not equal to 0, but here in the fixed it is take moment, so theta is going to be 0. So, actually this will be the curvature of the deflected curvature. So, slope is 0, I have wrote and this will be this deflected curvature. So, let me erase this. So, after this deflection curvature I got, then I can see that this curvature is having different orientation. The curvature of the deflected shape of the column changes its orientation. So, see the radius of curvature. So, this is this way and this is this way. What does it mean? That means at this particular point curvature changes. Curvature changes means, if you remember second week lecture, that is the point of contour flexure, and this particular point there is moment is also going to change. So, sagging, if you just put it in a the horizontal way, it is from the hogging to sagging, something like that. So, from this point of we may say that these points are the moment 0 point. Because why it is moment 0? Because this is change its curvature. As curvature changes, this point must be moment 0 from positive to negative. So, definitely there is a sign change in the moment. The moment is 0 over here, where there is this change of curvature. So, the length, the distance between this moment 0 point is nothing but the equivalent length of the column, right. So, these two point, we have to first find out where is the moment 0 point, and we have to find out that the length between them. So, if it is a hinge and hinge, we know the moment 0 will occur at the hinge itself. So, the L and this L will be equal. So, the fixed free, this is the moment 0 point and this is the moment, it has to be fictitiously say that is a mirror image, and so this is twice of L. So, third case, this is the fixed and free fixed. So, this will be the moment 0 point, because this is the curvature, this is the curvature, this is the curvature. So, these 2 points are the moment 0 point, this is 0.5 L. and whereas that other one which we have just now talked, this is the curvature and this is the curvature. So, these two are the moment 0 point, this is hinge already moment 0, it is 0.7 L. So, we now understood that this the whole philosophy behind this particular thing, how the moment equivalent length is marked with the associated with the equivalent length and the original length of this thing. So, now let us go to the a small problem. So, I have a beam of column of 100 by 300. So, I have two Ix value, Ix and Iyy value. So, out of that I have to take the minimum one, because the column will going to sway or the buckle in the weakest direction. So, I have to take this minimum one and then I have to find out this. So, if the both ends are hinge, so I use this formula pi, this is the E, I have given you the E value. So, this is pi square, E has taken 1 into 10 to the power 4, I is this one 25 10 to the power 6, and this is L square. L, E and L remain same as it is hinged. Now, in case of a fixed, LE is 0.5 times L. So, my original length was 3 meters. So, my L equivalent is 1500. So, that is why it is 1500 square. So, in case of it is both and fixed, it can have more capacity of taking load, because L is decreasing, the equivalent length is decreasing. If it is both ends are hinged, that is 274 kilonewton is the critical load. After that it is become unstable, and in case of the both ends are fixed, it is 1097 kilonewton is the critical load. After that it may be unstable. So, now I have a, suppose the same problem, I continue with the same problem with a 3 meter column which both end hinge. The first case, the column need to carry 5000 kilonewton, okay, so kilonewton load. So, here the critical load was 274. So, in same case if I go with that, definitely it will going to fail, because it is 5000 I have to take. How to take? So, I have to increase the cross section dimension. So, what should be the value if the B and D become the 1:3, the ratio is become 1:3. So, in that case I use the same formula, the P value, the critical load value is 500 kilonewton 500 kilonewton, the L become LE, the 3 meter. I have to find out how much is the I, E value is given. So, this is the I value, and with this particular ratio I can easily solve, and I can see that if my dimension of the column instead of 100 by 300, if I have 120 by 350, it can easily take the 500 kilonewton load as a the load that will not going to buckle. So, that will be the critical load. So, now there are the concept of the slenderness ratio, the Euler's slenderness ratio. We have to find out that this is the Euler's critical load. So, now in this particular critical load, I want to find out the critical stress. So, stress is nothing but the load by area. So, I divide that critical load by the cross section area of the column. The A is the cross section area of the column. Now, I just put the values of P, that is pi square E by L square, and then I rewrite that one pi square E at the top and the L square by I by A, moment of inertia by area, and then I am introducing another geometric property or the parameter of the column or any kind of a section, that is under root I by A. The under root of the moment of inertia by the area of the section, which is going to called as the radius of gyration r. So, if this under root by A is r, then L square by I by A is nothing but the L square by r square, and L square by r, I am sorry, L by L effective length by r is called the lambda or the slenderness ratio. So, finally, the critical values of the stress is nothing but the pi square E, and this whole thing now become lambda square, because this whole thing is now become lambda square, right. So, now see that the this I by A, under root I by A is called the radius of gyration. It is again a fictitious or the imaginary line or imaginary ring, where we can assume that in case of a rotation the mass is concentrated, or this kind of the rotational case the actual distribution mass is concentrated over there, and the lambda is nothing but the slenderness ratio. If lambda is very high, the column is long column, and lambda is smaller, that means it is not slender, it is bulky, so it is a smaller. So, it is the ratio of the LE effective length by the radius of gyration. Radius of gyration smaller means it is very cozy, very small sections, and that is why the lambda may be very high. Or radius of gyration very high means it is very fat, so it is kind of a lambda value is very small. Now, see how this lambda values will going to help us. So, this is the I am comparing the strength of these two sections. One is suppose a column of solid circular section and another one is hollow section. So, the area I have computed almost similar area. I have computed the moment of inertia of the hollow and the solid sections. I also computed the radius of gyration. See how I am computed. This is the I value and this is the A value and under root. Similarly, this is the, so I can say that this particular 100 mm dia circular section solid, the mass is concentrated almost about 25 mm around the center. In this case, I may say that the comparable area, but I may say that the mass is concentrated almost about 53.29 millimeter away from the center. So, it is much more wider. This ring may have the same almost same area with this particular solid, but as the mass is bit more the outwardly distributed, whereas in case of a solid section it is very cozy. So, I got the R value. Now, if I assume that for this particular problem, that is a 2 meter long beam column, and the E value is the Young modulus is this, then I can find out the first lambda like this. Lambda is 2 meter, the effective length by 25, that is the R. So, this is 37 and this is the 80. So, definitely 80 is much higher than 37. So, I may say that this particular column, the solid column, is much longer column with respect to this hollow column. So, finally the critical stress also can be found out. So, in case of the solid column, I computed the critical stress is 380 Newton per mm square, whereas in case of the hollow it is 1401 Newton per mm square. If I now multiply this with the area, I can find out the critical load, that PE. So, the thing is, if I use almost same amount of material, it is always better to have a hollow column and distribute the mass outward such a way that I found my slenderness ratio is lower. Why is lower? Because I have the higher amount of radius of gyration, and I can have the higher, as the slenderness ratio is lower, I can have the higher amount of stress value, the critical stress value. So, I have computed the slenderness ratio for steel and aluminum, putting their values of E. Steel is 2 into 10 and aluminum is 0.8 into 10 to the 4, 0.8 to 10 to the 5. So, and I have computed that how the slenderness ratio has drastically decreased the critical stress. So, this is in the y axis, it is critical stress, and x axis is the slenderness ratio. So, see how it is drastically. So, it is depend upon the material also E values, and this is depend upon the lambda values. So, now if you compare the one of the Egyptian temple, if you see the Egyptian temple, if you see the temple in Karnak or maybe the Luxor or maybe the Abu Simbel, anywhere there is a kind of a particular pattern or particular formation. The central aisle will have a clear story. Above that there is a clear story to allow the daylight. So, it has to be high, because this is the clear story. the clear storage windows are there. So you need a high column, and this papyrus capital will be there, as you know, and the others will be the lotus capital, as you understand from the, as you know from the your history of architecture. And rest, to create this clear story, rest of the portion will be lower, and so the you have some columns to support the slab. So you have two type of column, the central one is high and the wings are, or the flanks are the lower, and you see the dimensions of the, also from the plan, see the higher dimension in the lower, I am sorry, the central one, and the less diameter in the flank. Why? Because you have to understood that if you want to put the higher, the longer column, you have to increase the dia to take care of your critical stress, take care of the slenderness ratio, and take care of your the PE, that is the critical values of the forces also. So I have one small problem for you. This is a particular square slab of 5 by 5 dimension, which is supported a water tank, and I have given the unit weight, and so I have found out the critical what is, how much is the total load on each column, and I also found out the what is the compressive stress, and then I again found out the how much is the critical stress, which is 329 Newton per mm square. I found out the I value, A value, and all those. The dimensions of the columns are also given, 300 by 300. I found out the I area and the moment of inertia, I by A under root, everything I found out. And as it is a the column is effective length is 0.1/2 of the 3 meter. So this is also calculated, and I found that the critical stress is 329. Please remember this, 329 for 3 meter column, but my actual compressive stress is very less. So it is very safe in that sense. Now next is, suppose this particular the column length is 8 meter, not 3 meter, then how much is the critical stress? So the only change is this length. So I found out everything over here, and then the lambda is changing. Lambda initially it was something like 17, now it is 46. So critical stress become 46.3. So it was 300 something over there for 3 meter, for 8 meter it is 46. That makes me a sense. You see this particular structure, the water structure, water tank, you see they put the beams unnecessary. These are unnecessary beams. Why they put the beams? It is not unnecessary. This long column will not going to stable if there is no beam. This beam, intermediate beams, create the small diversion of the column, and the effective length of the column is smaller in that sense, one sense, and it is a breast also. So even these columns look like it is not holding any kind of a slab, not holding any kind of a ladder, nothing, just it is a ring kind of a connecting the each column, but it makes sense because it reduces the effective length of the column. Now you can calculate the effective length is now maybe 2 meter or 3 meter, something like that, but here it is 12 meter, 15 meter. Definitely with the huge amount of load of water, it will going to buckle, right. So that is all for today's lecture. So this is the reference I have took. The conclusion, I can say that the column can be classified into the short and long column. Shear is predominant for the short, buckling is in the long. Slenderness ratio is the prime geometric factor for designing a column. So in the next lecture we will go to the frame structure analysis and design. I have two homework for you. One is this, you have to find out the buckling load or the critical load for this 4 type of end conditions. The sections is given and the length and everything, E values are given. And the second one is that you have to compare the strength of a steel column, of a solid steel column and a hollow steel column. So both are steel, and the internal diameter of the hollow one is 0.7 times of the external diameter, and they have same length and both ends are hinge. So kindly do that, kindly try that, these two homework. Thank you very much.